Good day, everyone. This is Moe Shahram, and this is third lecture for Physical Science Survey, PSCI 10 at West Valley College. Today we are going to talk about Chapter 3 about work and energy, and we will cover the concept of work and concept of energy, and then we will talk about different types of energy, such as kinetic energy, potential energy, and their relationship with work and the work energy theorem. And then we will talk about gravitational potential energy, which has a lot of application, and talk about conservation energy, which energy is always conserved and is neither destroyed or created. It only transforms from one manifest to another. And then we will move on to talk about the concept of power, and from there we will look at different forms of energy and talk a little bit about the statistics of energy consumption in the US, and finally talk about renewable energy and basically close with a little bit about renewable and nuclear energy. Of course, we will talk more about nuclear energy later on down the road. So the concept of work is very simple. When we learn that if you apply a net force to an object and the object moves, by just moving that object, you are actually doing some work. The concept is very easy, but there is some subtleties there. Work is defined as the force applied and the distance an object is moved, provided that force is along the line of direction of the movement. So in other words, if you apply a force in a different direction of movement, that force necessarily do the work for you. Maybe portion of that will do the work, but in some instances it doesn't even do any work. So we'll see about that in a minute. So the definition of work is force times distance along the line of the motion. And the unit for that is the unit of force, which is Newton, times the unit of distance, which is meter. Remember, the unit of force Newton was kilogram meter per second square, times meter, so you will have kilogram meter square per second square. And we just named this after Mr. Joule in honor of him. We call this joules. So the unit for work is joules. We need to consider two important factors, that the force that is applied and then the movement of the object. Is it in the same or opposite direction of the force? When you actually apply a force for, you put your gas pedal and your car moves straight, there's work done there because the energy that you burn the gas to push the car with the force, it's times the distance that you cover, you actually doing your work. Now, while you're driving and you hit the brake, you apply brake, so the force is actually now it's slowing down the car, but still you're doing work. It still is along the line of the applied force, but in the opposite direction. So it is important to keep that in mind, because look at this gentleman. He is pushing the wall and he's spending a lot of force to do that, but he's going nowhere, because actually he's not doing any work, because the object, which is the wall, is not moving. So D is zero. Distance is not covered, nothing, zero. So the work done is zero. Although he may be sweating, but hey, there's no work, no positive work done. Now, as opposed to this gentleman who's pushing this block a distance d, and the force is applied in the same direction, so the work is actually performed here. When you lift an object from the ground, you're doing some work against the force of gravity. Okay, for example, here you have this barbell which has 25 kilogram on one side, 25 on the other side, so your mass of this is equal to 50 kilogram. The force of gravity that you're countering is Fg, we know from previous chapter, is mg, and that is equal to 50 kilogram times, let's say, 10 meter per second square, and that is 500 Newton. So that's the force. Now the direction is upward, so you have work is equal to Fg times the distance here, d, and that is equal to 500 Newton times what is it, 2 meter here. Okay, so what you get 1000 joules. So that's the amount of work you perform to push this barbell up. Sometimes you may apply a force not completely in the same direction of the motion, but in some angle. And we'll do example in a minute. Not all this force is producing work. Portion of this force is only effective to produce work, and we'll see that in a minute. Or you may be pushing in an angle on an object like this lawnmower with an angle of theta. The force that you're applying is greater than the force that is really doing the work along the line of motion. So a portion of that force, which is F times cosine theta, is really effectively doing the work, times d, which is the distance. So let's look at these scenarios here. You have this fellow pushing this cart, and it's moving in the same direction as applied force, so therefore work is done. In this case, you're just carrying a weight, or yourself, you're just walking. There's no work done in this case because the force of gravity of your weight is downward and the support or normal force is upward. So those forces are perpendicular to direction of this, and that is no work done. When you lift something, however, you are moving that object in the same direction as you apply the force, therefore you do work, just like this fellow here. So if you're just carrying it, you're not doing any work on this. Okay, so keep that in mind. And when the waiter or waitress brings you food from the kitchen to your table, basically he's holding the tray, and the tray, the force that are involved there is force of gravity downward, and the support or normal force upward that we learned about it, and the motion is forward. So this is perpendicular to that, so there is no work done. Okay, now let's look at this scenario here that we just showed you, and this fellow is pulling this cart at an angle of 30 degrees. When you have this situation, you are actually exerting a force of 50 Newton on this direction, okay, and you're moving this let's say to 30 meter. So d is equal to 30 meter. So what you want to do is find out what is the component of this on the same direction of the motion. So you project this vector here and you get this component let's call that Fx, which is in the direction of the motion. So what is Fx? Well, this angle is 30 degrees. So cosine of 30 degrees is equal to what? Is equal to this Fx divided by the F. So what we have here, the component of Fx is equal to F cosine of 30. Okay, you may want to review your trigonometry, properties of triangle. Now, this is the component that applies. So the work done is equal to this component, which is F cosine 30 component, times the distance, which is 30 meter. Okay, this thing changes its color by itself. So that's basically what the work done is. So we know the F is 50 Newton times cosine of 30, which is I believe 0.87, and then times 30 meter, and that would be your work done there. So 50 Newton times cosine of 30, that's Fx, and times the 30 meter, so you get 1299.0 joules. Now, if you were to pull this along the line of motion, then this cosine of 30 goes away. You just have to multiply 50 by 30 and you get 1500. Force now that is applied is 50 Newton rather than 43.3. A lot of time we do work against the gravity. We basically lift things up, and that by itself it's work because the gravity is pulling everything down. We also do work against the friction, the air drag, for example, the friction between two surfaces. You do work against that. In the case of gravity, it's the weight, which is a force. We already talked about that, and you try to lift that weight to a distance, the height, force of gravity or weight, times the height that you lift this thing up, and that's called work. Mg times the h, which is the height that you lift this object. To answer this question here now, work is done in lifting a box. How much work is done in lifting a box that is twice as heavy and the same distance? Twice as heavy, the weight is twice. You just have to multiply that by the distance, which is the same distance, so you get twice as much work. When you do work when pushing a cart with a constant force, if you push the cart twice as far, then the work is equal to force times distance. So if you multiply this by 2, the work actually multiplies by 2. So now let's see, what is energy? We talked about work, but how does it relate to energy? Well, it turns out that energy is ability of a force to perform work. So when you are pushing an object, you are spending energy to push that object. So the energy in your body is converted, and then you apply a force, and that force is doing work, pushing a cart a certain distance. Okay, so energy is ability of force to perform work. Or you can say measure of ability of force to move a body. As you can see, there's a relationship here. Energy and work, it's pretty much of the same nature, because you need to spend energy to do the work. So when you do a lot of work and you spend a lot of energy, your energy decreases. Your system is doing work. But when the work is done on the system gains energy. For example, when you eat food and your system is gaining energy. So therefore, when you do work, you basically going through a process that energy is transformed from one object to another, because now work and energy are pretty much of the same nature. And that is the concept of work and energy having the same unit, and that's joules. Now, what are the different types of energy? In general, we have potential energy and kinetic energy. For example, start with kinetic energy. Remember, in previous chapter, we talked about momentum. We said anything that moves has momentum. And we talked about P is equal to mass times velocity. And that was momentum. Now we say anything that moves also has kinetic energy. And that kinetic energy is equal to, let's call it EK, kinetic energy, is equal to 1/2 mass of the object times velocity squared. Okay, so you see the difference between these two. Now we want to see what is the unit of this energy. Remember, the unit of work was what? Unit of work was joules. Now, unit of energy here, look at it. You have mass, which is kilogram. Unit of velocity is meter per second. Be meter square per second square. I put the units always in a bracket, so it's not part of the equation. So distinguish between that. So now you see that that is the same thing as what we just defined as joules. And there are many different examples of the kinetic energy, anything that moves. And you can see some examples down here in these pictures here. Let's ask this question. Suppose a mouse and a cat are running, but they have the same kinetic energy. Which one is moving faster? Whenever you have these kind of questions, the best thing is to use the equations, the formula that we learn, to guide you for the answer. For example, for the mouse, the kinetic energy is 1/2 m of the mouse v of the mouse squared is equal to 1/2 m of the cat v of the cat squared. So 1/2s go away, left with m and v's and m. So we know that the mouse mass is small, and we know the mass of the cat is bigger. What has to happen here for this equation to hold? Well, if the mass of the mouse is small, its velocity must be bigger. But if the mass of the cat is bigger, the velocity must be smaller. You use the equation to guide you. Another example here, so you have a 1 kilogram ball is fired from a cannon. What is the change in the ball's kinetic energy when it accelerates 4 meter per second to 8 meter per second? What do we know here? We know the mass of the cannonball is 1 kilogram and velocity goes from 4 meter per second to 8 meter per second. There's a change in its kinetic energy, because kinetic energy is, second part is mv squared minus the mass doesn't change, so minus 1/2 m v1 squared. So that is a change in kinetic energy. You plug in 1 kilogram, which is the mass of the ball, times 8 meter per second squared minus 1 kilogram times 4 meter per second squared, and the ball's change of kinetic energy becomes 32 joules minus 8 joules, which is 24 joules. Another application of this kinetic energy and work is when you are applying some sort of a brake force to stop an object. A simple thing is your car. And this is actually one of the questions that when you go get your license in a DMV, one of the questions always is that what happens to your braking distance if your velocity is doubled? A lot of people get that wrong. The braking distance doesn't double, it's quadruple. So let's see what happens here. Suppose you're driving at 30 miles an hour, okay, and then you have to stop. So hit the brake, your braking stopping distance, you can measure what it is. Say a certain distance. Now suppose you go twice as fast. What happens? We can find out, because your kinetic energy is equal to 1/2 m depends on v squared. If your speed is doubled, your kinetic energy is quadruple. It's 4 times. 2v squared is equal to 4v squared. So it's 4 times, right? Now, how does it relate to stopping? Well, we know the kinetic energy is converted to stop the car. So that's equivalent to the work that is done. And that work is force times distance. And that distance is your braking distance. And this force is force of the brake. Okay, so let's call that the FB. So this FB times D equal to change of energy, because now you go from 60 miles per hour to 0, 30 miles per hour to 0. So that is what we are looking at. So it's change of kinetic energy. But in this case, because you stop, so it would be your initial velocity. This thing is called work energy theorem, okay? At this point, if you know, for example, you're going at 30 miles per hour, whereas you go at 60 miles per hour, your velocity is squared. So here would be 30 squared in this case. In 60 miles per hour would be 60 squared. And that affects your braking distance, because the force of brake doesn't change. The mass of the car doesn't change. The only thing that changes is the braking distance, and that's why you need to keep your distance from the next car in the highway as you go faster and faster. So this is called work energy theorem, and its simple form, it's force of times the distance, which is work, is equal to change of kinetic energy. Now let's talk about potential energy. Potential energy is when you are actually lifting an object against the gravity. By doing so, you storing energy in that object. Why? Because when I lift an object to this height from, say, my table, I am storing energy in it. That's called potential energy. If I let go, it's going to fall down with kinetic energy and hit the table. The potential energy sometimes is called positional energy, because it depends on the height of the object with respect to ground, or with respect to a reference. You need to specify a reference. Your reference could be the top of the table. You could choose a reference as the ground level, or if you're in a high rise, you could choose a reference as the floor below you. That's arbitrary. But once you choose your reference, you can find what would be the potential energy of any object that is lifted a certain height from that reference point. Look, force of gravity times height, force times distance. We just defined that. That's work. That's the definition of work. Now we are doing against the gravity, so we're going up. This is also potential energy. We call that EP. Now, force of gravity, we know what it is, mg times h. Potential energy is equal to mgh, simple. Mass of an object times the g, acceleration due to gravity, times the height from a reference. Very simple. And that's equivalent the work that you do to take this up to that level. And that at that point you have stored energy in there. So here's an example. How much work is done lifting half a kilogram book to a height of 1 meter? Work is equal to mgh, or potential energy, same thing. So 0.5 kilogram times 9.8, here we use 9.8, you could use 10, times 1, that's 4.9. Could be, if you use 10, it would be 5 joules. Make sense? Important is to know where is your reference, because the height that you use, this h, is from your reference to that height. For example, you take an elevator in a high rise. Say your mass is 80 kilogram. What would be your weight? 80 times 9.8, so that's 784 Newton. Your force of gravity or weight is 780 Newton, as opposed to your mass is 80 kilograms. So 80 kilograms is what? Is about 180, 90 pounds. Then you go to 10th floor. The height is 40 meter above the ground. So your ground is the reference. You multiply that weight or force of gravity times that distance or height, you get 31.4 kilojoule. So that means times 1,000. At the 9th floor, you're only 4 meter above the ground. So you have the same weight times the height, which is 4 meter, which is 3.14 kilojoules. So that would be your potential energy at 9th floor as opposed to 10th floor. Some examples of gravitational potential energy. You've seen some water tanks, some around, some cities or rural places. You pump the water up there, the potential energy that's stored there, and then you pipe it back down for consumption, and it has a certain amount of pressure. The water flows from the higher potential energy to the lower potential energy. And the potential energy converts to the kinetic energy as the water flows down. Another thing is when you have a dam. Build a dam to raise the level of the water high, and then you use the potential energy that is stored there, for example, turning a turbine. Different examples, for example, you go upstairs. You climb upstairs, you're building up potential energy, gravitational potential energy. Now, important point here is that potential energy, as you can see, depends on the mass, g, which is constant, and the h. H is the height from a reference. For example, looking at this ball at this point, up here it has 50 joules. Down here it has 0 joules potential energy. But it's independent how the ball has gone up. It doesn't matter how you took it up there. As long as you're a height h from the ground, so it only depends on the initial reference point and the height directly above it where the object is. Here's an example that we choose a reference, let's say at this point here. So I have a coordinate system here which I assigned a 0 reference at this point. So this ball at this point doesn't have any potential energy because the height is 0. But if I take it up here, it would have an energy that is mass times g times 50, let's say 50 meter from here to there. And we call that a positive. If I choose my reference here, then anything below it is going to be negative. Like if you dig a well from the ground level, so you go down the well, so you kind of have a negative potential energy with respect to ground level. So here you go down and you have negative potential energy. Very important, choosing the reference, you choose the reference conveniently and it's arbitrary. There are different forms of potential energy. And if you squeeze a spring, you actually storing the potential energy. You're increasing its potential energy. And when you let go, it's going to expand. So it's going to turn into a kinetic energy because now it moves. Or if you pull the string, same thing. You just let go, it just contracts. And many, many different combination of these situations, like, bow and arrow, like, when you go on a swing. In the chemical reactions, we have potential energy. We build potential energy in some chemical reaction. We'll talk about that later. Electromagnetic potential energy, we talk about that later. And nuclear and mechanical. Let's say we have a bow and arrow, and you need 60 joules to draw the bow. With 60 joules, you do that much work to draw the bow. And then you release it. All that energy transforms into an arrow which flies off with kinetic energy. It turns out that 50 joules is the kinetic energy of the flying arrow. So what happens to the remaining? Well, when you stretch the string, you kind of bend the bow. The bending of the bow is actually you are doing work against the molecular bond of the bow. They move around, and some of that energy turns into a heat because they kind of rub against each other to allow the bending of that bow. And that way some of that energy gets wasted in the form of a heat. So energy doesn't gets destroyed, it just gets transformed. So as we mentioned earlier, it doesn't matter which path you take to lift an object to a certain height. It's the height that is important, not the path. All of these paths gives you the same potential energy as long as you're at this height from the ground. Very important concept in dealing with energy is the conservation of energy. Okay, it's a very fundamental law. Remember, we talked about laws, and it's been proven over and over and over that the energy is not created nor it's destroyed. It basically transforms from one form to another. So if you have a system, the total energy of that system stays the same, remains constant, no matter what happens inside that system. Now, that system may interact with outside. Some of the energy may escape outside, like heat energy. But if you have a means to account for that, then you'll see that the total energy still remains the same, just like that bow and arrow. So the bow and arrow are a system. So when you pull it, the bow is bending. A little bit of a heat is generated and the heat is escaping. But if you have ways to measure that, the whole thing turns out to be the same energy that you put into pulling the string. Okay, so total energy is going to be constant. It only transforms, very important, from one form to another. All right, so when we're talking about mechanical energy, we are specifically talking about kinetic and potential energy. And the total mechanical energy is conserved. We know now the potential energy is mgh, kinetic energy is 1/2 mv squared. So total energy before has to be equal to total energy after. Of course, we talk about ideal system. As I said, in the process, some of these energies are escaping in the form of heat. So that's not an ideal system. If you have ways to capture that amount of energy, still the conservation energy holds. Let's look at this example. So now you have a ball that is raised to a certain distance up here. Let's say it's 90 meters. You kind of build up a certain amount of potential energy, 600 joules. You hold that ball right there. Now you're storing 600 joules at that position for that ball. Now let go. The ball starts dropping. Its potential energy going to reduce as it's dropping because the height is reducing. Let's say it gets to a height of 36 meters. So the question is, what is the velocity of this ball at that position? Well, we can use this conservation of energy to find that. We know mass is 0.66 kilogram, that's given. We know the initial height is 90. We know that initial potential energy is 600 joules, that's given. What we don't know at this point, what is the potential energy, what is the kinetic energy? But we can find that out. But we also know that conservation of energy holds. So total energy is equal to potential plus kinetic. Let's find out what the potential energy is. Easy. Mass we know, 0.66 kilogram. G, 10 meter per second squared. H is 36 meter. So you have 237.6 joules potential energy at this point. Knowing that the total energy is conserved, so starting with 600, that was total energy at up there, 600, because kinetic was 0, so total is just 600 at top, minus this potential energy, which is 237, so you're left with 362.2 joules. Potential energy is transformed to kinetic energy. Kinetic energy formula is this, potential energy formula is this. That amount is transformed from kinetic to potential. Look at this relationship. If you, we know the mass didn't change, so you can get rid of the m. So you're left with 1/2 v squared is equal to gh, or v squared is equal to 2gh, or v is equal to a square root of 2gh. And that's what we're looking for. What is the velocity at this point? 26.8 meter per second. So please go over and review these examples. A very important example is a pendulum. When you look at the pendulum that is hanging from a string, and you pull it to the side and let it swing back and forth, what happens? Well, let's assume that this level, it's ground level, 0, okay? So when you pull this to side, what are you doing? You're actually increasing the height of this h. And let's say this is a mass m. You are actually building a potential energy here, mgh, at that point. Now, you're holding this bulb, not letting go yet. Kinetic energy, let me use the same color again, EK is 0 because it's not moving. Then you let go. It comes down here, H is 0 here. In this case, EP, potential energy is 0. So EK must be equal to the same as what you started with, mgh. And then it goes back to this side, again goes up to height h, and again you have the EP is equal to mgh, and EK is equal to 0. So this transfer of potential kinetic constantly happens as you swing back and forth in this pendulum. So halfway here, halfway down, at this point, your EP is going to be equal to EK because of the conservation of energy. Same thing happens when you have a spring that is swinging back and forth from a equilibrium position, or if you're climbing up to a hill and coming down. At this point, potential energy, as you can see the bar graph here, the bar graph here, you having a velocity to go up there. Kinetic energy is spent to get you up there. At this point, potential energy is 0 because you are at ground level. At this point, all the energy, kinetic energy that you spend to get up there becomes your potential energy. And then when you come down, you gradually lose the potential energy and gain kinetic energy until you get down here with the same speed. And this skier, look at the amount of energy transfer here. Kinetic energy, top of the hill is 0. She has 50,000 joules, 50 kilojoules here at 100 meter up there. It gets to this point, kinetic energy builds up 20 kilojoule, and potential is reduced now to 30 kilojoule. At this point, it is 30 meter high, so kinetic energy is 35 kilojoule, potential is 15 kilojoule. It goes up. At this point, is kinetic energy just pushes up all the way to here. She has 20 kilojoule of kinetic and 30 kilojoules of potential. And then when it reaches down here, she has 0 potential but 50 joules from top, provided she didn't lose any heat due to rubbing ski against the snow. Of course, it does. So you lose some energy down the road. So when you look at the pendulum, it's interesting because when it gets here, it has maximum kinetic energy and minimum potential energy. If you look at the curve of the energy with respect to distance, and this is a distance, horizontal distance, at this point, red one is the maximum kinetic energy, and the blue one is the 0 potential energy. But if you pull it up there to hold it, you have maximum potential energy at this point and 0 kinetic energy because it's not moving. As you can see, as they swing back and forth, at some point here and some point there, the kinetic energy and potential energy are equal. Now, if you look at the graph as a function of time, you also see that these things swing back and forth. The kinetic energy and potential energy complement. But important thing is, at any point of time, if you add the potential energy amount here plus the kinetic energy, you get total energy, which is this green line up here at any point. By the way, this kind of behavior is called simple harmonic motion, this kind of oscillation. Now let's talk about the concept of energy flow. How does energy flow in nature? Well, we just learned that energy converts from one form to another. A very, very important and essential example is the photosynthesis. So you have the sun energy hitting all the planet, and the planet basically goes through the photosynthesis reaction. Obviously, it absorbs the water from the ground, and you need the carbon dioxide on the atmosphere. So it absorbs carbon dioxide and takes the energy from the light radiation and turns that into a sugar and oxygen. Releases oxygen and builds up sugar in vegetation. So as you can see now, the energy has transformed one form to another. So looking at this flow, you start with, say, photosynthesis. We eat the vegetable, fruits. Animals do that too, and sometimes we eat animals. Animals eat animals. Some of us do, some of us don't. Then we spend that energy that we gain, the sugar and carbohydrate, and we start doing things, work, okay? We sweat it. We give off some of that in the form of a heat to the environment. We can actually see that with the infrared camera, how much heat we are dissipating. Or we burn energy to warm our house, and then some of it escapes to the air, and Some of it gets reflected back by the atmosphere. And if a lot of it gets reflected back, then what do we have? We have global warming. Because what is causing these reflection is a lot of pollution, these toxic gases that build up in the atmosphere. And they kind of reflect a lot of that energy that's supposed to be released to the outer atmosphere. They get trapped. Now we have another concept to introduce. So question for you is that suppose you go to the parking lot and you want to go to your class. One day you're not late, so you walk from your parking to your class. Another day you're late, so you run. The question is, and you go through the same path. Question is which way you do more work. Now this is something that a lot of people get it wrong because it's something counterintuitive or as a misconception there. The answer is actually you do the same amount of work. The work is the same because you are actually covering the same distance. What is different is, or how do you spend your energy to do that work? How fast or how slow? So there is time involved here. The rate of doing the work is different. When you run, work at the faster rate or spend energy at the faster rate. When you slowly walk, you spend the energy or work at the slower rate. That's where the concept of power comes to play. Power is totally different than work. Power is work done in a unit time. How fast or how slow you do the work. That's a measure of power. So when you run, you spend more power because the time you spend was less to do the same work. In equation form, what do we have? Power is equal to work per time, unit time. Unit for it, we know the work unit is joules, and we know the unit of time is second, joules per second. And we call that after Mr. Watt. So we call it watt. And we show it with W. Now, too many W's now. Remember, we had the small w for weight, and we had W for work, and now we have W for watt. So keep track of these. What can I say? How many watt? 100 watt. The bulb has 100 watt power. Some of these bulbs are rated 100 watt. So it means that it uses 100 joules of electrical energy in 1 second. Energy spent in time. Apply 1 Newton force, raise an object 1 meter in 1 second. Then you actually spend 1 joules per second, which is 1 watt. There is another unit for power, and it's called horsepower, because it used to measure the power by power of a horse, how much a horse can pull. All right, and it turns out that if you have a horse that pulls up a 75 kilogram 1 meter in 1 second, that is called 1 horsepower. So you use that and they convert that to watt, and it turns out to be 735.5 watts. So that's a conversion. We use both. You know, some motors you see, they say a 2 horsepower motor, certain amount of work in a certain amount of time, rated at 2 horsepower. Or you can convert it to watts if necessary. So use this conversion factor. Example, 300 horsepower car. You've heard some cars are 400 horsepower. Or if you have a motor that runs 2 horsepower, it can do twice as much work than 1 horsepower in a given time. So that's basically meaning of that. Now let's quickly review all the units that so far we've talked about, and just have them all in one table here for a reference. Force was Newton, kilogram meter per second square. work was joules, Newton meter. Same as energy. Energy was joules, Newton meter. And power was watt, joules per second. Okay, so let's do an example here. So you're applying 250 Newton to push a car that is stalled. So you want to push it 10 meter in 20 seconds. So we want to find out power expended in watt. We know force is 250. We know distance covered is 10 meter. We know the time is 20 seconds. We want to find out how much power is spent. Power is equal to work per time, per unit time. So work is force times distance. We already know that. Time we have. All we have to do just plug those numbers. 250 Newton, 10 meter, 20 seconds. You get 120 watt you spend to do this pushing. What if you're lifting something and you spend 8.5 watt of power to lift that half a meter in 1 second? How much work now you do? No, it's kind of a reverse of the previous one. So we know now the power, and we want to find out the work done. 8.5 watt, distance is half a meter, time is 1 second. Let's find out what the work done is. Okay, work is equal to power times time. Okay, so we use that equation. 8.5 watt times 1 second, so 8.5 joules. That's the amount of work. You have the force times distance is work. From there you can find what the force is, because it's asking how much does the book weighs. That means the weight, the force of gravity. So from this relationship, force of gravity is equal to work divided by distance, and that's 8.5 joules divided by 0.5, and that's 17 Newton. So please review all these carefully. So remember that Fg is same as weight. Another important thing is that we all encounter is paying our PG&E bill. Say your electrical bill says you spent 1200 kilowatt hour. Now remember, when you see this 1200 kilowatt is a unit of power, but it says kilowatt hour times hour. What does it mean? That's the unit of energy. That's the energy spent, not the power, because you have this time multiplied by it. If the rate of utility is 35 cents per kilowatt hour, that's what they give you, somewhere between 25, 35, sometimes 45. How much it will be your bill? You can look it up in your PG&E bill. You can see these numbers. 1200 kilowatt hour. So now, kilowatt hour at the rate of 0.35 or 35 cents per kilowatt hour, the kilowatt hours drop out, so you pay $420 for your consumption of electricity. So looking at the flow of energy, you know that a lot of food energy, it's going through this energy cycle. From the photosynthesis, we gain a lot of sources of food, good food, healthy food, as you can see here. A lot of vegetable, nuts, There's a lot of carbohydrate and as well as sugar in here. But they're natural, okay? And then you have different types here. But you also have these other ones that is full of sugar, additional sugar that added. And those are basically not healthy for you. Anyway, so now let's quickly talk about some statistics in energy consumption around us in US. If you look at the chart, this chart is done in 2020, and Energy Information Administration put up this chart. As you can see, most of our energy consumption is from petroleum and natural gas. Some, about 9%, is from nuclear power, 10% is still from coal, And altogether, renewable is about 12%. What do we mean by renewable? Something that doesn't exhaust itself. It keeps reproducing. It is available. For example, the solar. I mean, sun is still available, right? 5 billion years from now will be available. Wind, it's there, available, always. Biofuel, wood, hydroelectric, and so on. So 12%. Out of these, 11% is solar and 22 hydroelectric. Damn, wind is a good portion. So let's look at some of these. If you go look at the trend of the energy consumption from 1950 all the way to now, that's about 70 years or so, the renewable has gained some grounds here. Nuclear has been pretty much constant since 1990, hasn't changed. The petroleum still trying to reduce a little bit, but still there. Natural gas actually has increased. Coal, thank God, is decreased because that's the major source of pollution. And then if you look at this one, by major sources, energy production. So the previous one was energy consumption. This one is energy production. Renewable is gaining grounds, but not as much as we want to. Nuclear is still same. It's gone up and down here. And crude oil and natural gas is increased, and coal is decreased. And here is another, for the production of energy, the bar chart. Natural gas is obviously it's the highest. Wind is around here, but solar is somewhere inside here, so it's still very small portion. Petroleum, well, oil we have to extract from the ground, okay, and as a result of organic sediment, over time, under pressure and temperature, the bacteria they turn things into oil, and then we extract that. We have been using that for over 150 years now. Natural gas, a lot of that's available underground, and usually they go hand in hand. So whenever you drill an oil field, there's always natural gas there too. And the coal is major source of pollution and impurity. You burn it, produces ash, sulfur dioxide gas, and so on. So all these are fossil fuel, and we should kind of reduce them as much as possible. Fracking, to get natural gas, you inject high pressure water on the ground, and then you kind of frack the ground, and the natural gas finds itself back here through the pipe and goes up, and you capture that up here. And there's potential, for leaks and contamination. And potentially when you frack a lot of areas, what you do, you disturb the plate tectonics. We'll talk about that in geology. And you can potentially provoke or induce earthquake. You have geothermal, but that is site specific, certain site near the volcanoes. When lava is closer to the surface of the earth, you probably get hotter ground, so you can use some of that to heat the pipes with the water, and then use that heated water and to turn it to a steam, and then you can do a lot of things with that. Turn a turbine, for example. There is one specific site in Hawaii that uses the geothermal. Not many of those around. As I just mentioned, you push water here, and then the water is collected back up, it's heated, turns into high pressure steam, and can basically turn a turbine, and then that generates electricity. You can use hydrogen, get the hydrogen from the water, liquefy the hydrogen under very cold temperature, and store it and burn it. Now it burns very efficiently, but it's flammable, and it's dangerous. Renewables are the best bet for us, and there's plenty of those. Dam are one of the sources of renewable, provided the climate, cycle does what it does. But some of that has changed, as you will see. We collect the water to a higher elevation, and that stores a lot of potential energy. And then we release that to turn the turbine. And we're going to talk about turbine later on in upcoming chapters. So that kind of throws off the balance of the nature to some extent. The other problem is when we are going through droughts, the level of water reduces, as you will see in Hoover Dam. I'll show you a little bit later. And that causes a problem. We have to kind of be mindful of these and mindful of what impacts can put on the agricultural land, because you may destroy some agricultural land and you may affect the climate. All of that is a possibility. Idea is that you funnel these huge amount of potential energy that built on this part of the dam through a tunnel here and the gate, and then you'll have the turbine to turn. Once you turn the turbine, it generates electricity, and then you send that electricity through the grid. Here, for example, is a picture of the Hoover Dam. Notice the level of water. This is a recent picture. You can see that the level of water was up to here, as you can see the contour here, and now it's probably 1/3 down, and that is causing trouble already. Pressure that you need to turn some of the turbines down below here, and that was in the news actually. You can see the problem there because of the droughts we have. There's another type of renewable energy, and a tidal energy. When you are in a situation that you have a river connected to the ocean, and the tides that rise up and go down basically causes the water to flow back into the river or go out from the river. Every time that happens, if you put some sort of a device that can turn as the water is kind of going through, you can generate electricity from that. But that changes, every time we have a high and low tide. The direction of the water will change, and then, this has to be bidirectional. So they have one good one in France. Here they use that to generate electricity in Rance River. Sugar, you can basically, if you ferment it, you get alcohol. That's how they make wine. You ferment the sugar in the grapes and you get alcohol. Now you can do the same thing because there's sugar in wood, there's sugar in corn, but you get ethanol, when you ferment that. And then you can use that to burn. Of course, this process is kind of expensive. It's not a very good source of energy. Biomass, you can burn material, the wastes, agricultural waste, urban waste, whatever you have in forest, and basically use that heat that is generated, convert it to electricity. Remember, in power plants you usually need an agent to boil the water and turn it to a steam. But once you have a steam, then you have an agent that has a lot of pressure that can be used to turn the turbine. Of course, burning these things creates a lot of pollution. So that's the problem with that. Nuclear fission, which we will talk extensively in one of the upcoming chapters, is a very efficient ways of producing energy, because with a small amount of uranium or plutonium you can generate a lot of heat and generate electricity from. We will cover this later on in detail, but the problem here is a potential leak or meltdown or storage for the waste product, because the waste products are all radioactive and is very dangerous. Wind energy, very interesting one. The requirement for that is you have to have 15 mile per hour wind at least. But in certain areas that wind is available, especially in rural hilly area, because the wind at the higher elevation is higher, and you have 15 to 20, 30, 45 miles an hour wind, sometimes even more. So that's a good source. We use this in rural area when nothing else is happening, and that provides a lot of good energy. And by just turning the blades by the power of the wind, you're turning a turbine inside and generating electricity. This is what Ultima Pass, and look at all these wind turbines here. You can even put those near the shore in the ocean, because there's always the wind between the ocean and the shore, because the difference between the temperature of the cycle of temperature on the water and the earth provides a continuous flow of the wind, which we will talk about that when we talk about the weather, and that continuously provide the wind that it's useful to turn these turbine and generate electricity. So that's offshore. Now, some of these wind turbines are huge. Look at this. Even the helicopter can land on top of it. Look at that guy right there. These are, size of these huge trucks, maybe even larger. And they're roughly around 5 megawatt. What does that mean, 5 megawatt? Well, it can produce a lot of energy, okay? So 5 megawatt can produce about 1.2 million kilowatt hour per month. And that's enough to, cover thousands of home energy consumption with one of these guys. So it's a good source of energy. Then we got to my favorite, solar and photovoltaic, using sun energy, which is abundant, it's there all the time. Convert that to electricity by means of semiconductor. Semiconductors have this property that we take advantage of, and I'll talk about that in a minute, that converts the sun radiation energy into electricity. You can also use these passively, in other words, use mirrors, focus the sun light into a reservoir of the water and heat the water. There are many ways you can use sun energy, but the important one is the solar photovoltaic. Of course, the efficiency of these are not that great. The panels that collect sun, the amount of energy that they collect and the amount of energy they produce, their efficiency is about 20% at the best. But that has been improved since last 10 years, which I was involved in this industry. We had panels that are 15% efficient. Now we have panels that are 20% efficient. So it's improving slowly, but there's always a bottleneck. There's always a limitation, because the semiconductor atomic structure, it's actually doesn't allow much of an efficiency these days. So we can incrementally introduce the efficiency by other side means, but this limitation has to do with the atomic structure of the silicon. We'll talk about that a little bit when we talk about electricity and magnetism. So the idea is that theoretically, if you take a portion of Arizona, which has a lot of sun, this portion, this much, maybe 1/3 of it, maybe 1/4, and put those solar there, you can feed the entire United States consumption, theoretically. It's just to give you perspective at how much solar panels you need to feed the whole country. The problem is that obviously that's impossible. You can't take over 1/4 of the state. Number two, how can you transport this energy from here to Maine, for example? It costs a lot more than what you have these days to produce energy. So doesn't make sense. The beauty of the solar photovoltaic energy is that they are localized. In other words, on every house, every building, every commercial building, every school, if you have a solar panel energy, you can use that energy right there. You don't have to transport it thousands of miles from power plant to next city. And that is is a distributed form of energy. Of course, you have solar farms and this and that. Those are fine, but when you use a solar energy on top of your roof, you constantly use that right away from the sun to your water heater or your heater or your electricity. So here are some example of solar farms that are out there. It's a combination of solar and wind, which is nice. And here what we have in our school. We didn't have this 7-8 years ago. Now we have them all there. They give you nice shaded parking area and then produce electricity right where we want it. So there are some commercial, and if you flying over the cities, you can see there's a lot of roofs that are empty there, that you can potentially put a lot of solar panels out there. So you don't need any additional real estate. Some of these are trackable. In other words, for more efficiency, they kind of track where the sun goes through the day. So they get more sun radiation converted to electricity. Okay? So the concept is that you put the solar panels on the roof and you bring that through what we call it an inverter, because the solar panels are producing a DC current, direct current, and we're going to talk about direct current, alternative current later on. The DC current has to change to AC current because what we get from the grid, from the PG&E, is AC current. So in order to be compatible, we have an inverter that changes that to AC and feeds your service panel, and then you use the electricity through your service panel throughout your house from the roof. And then at night, you use the grid. Of course, you can have enough solar panel at the roof that during the day you generate a lot more than what you need to use in your residential. The remaining goes back to the grid, so you sell it back to the grid. Utility company gives you credit for that. Your meter turns backwards. It's just like bookkeeping. So it knows how much you feed back to the grid, and then at night you can use from the grid against your account. And that way you end up paying nothing. If you design the system that is for all your consumption, you end up paying probably $12 a month just for the connection. As you can see, many places have been already installed and using the solar panels on their houses or businesses. The sun hits the surface of this semiconductor. What is a semiconductor? Well, we have silicon. Silicon is abundant. We get the silicon, we melt it, we turn it into ingots, like cylinders of 5 inches, 7 inches, 8 inches, 10 inches, And then we cut them like the bologna. Of course, you have to do some processing, introduce impurity. The electrons in those starts moving and conducting and creating a current. Okay? And once that happens, then you connect these cells together and you put 60, 70 of them in one panel and bring out 2 leads, and that 2 leads gives you 30, 40 volts, and add about 20 of them, you get a lot of current and voltage out of it. Okay, so this is called a cell, this is called a module or panel, and then when you have a whole bunch of them, we call it array. So here's the inverter. The DC current that comes here turns into AC current, and you use it whatever that you need. The excess you push back to the grid, and at night when there's no sunlight, you need more, the grid will give you back against your account. And here's another graph that tells you that, the sun during the day generates a lot of, power here. At night, nothing, okay? But then you have, utility companies, they charge you a lot during the day, their peak days, peak hours. So those are the time that you generate a good amount of electricity. So you offset all of that. Then at night, obviously, you use some from the grid. Nowadays, people are even talking about, what if I, have a blackout? So maybe I should have batteries so that I become independent. And then if the, PG&E turns off the power for a few days, I use a battery backup, use it for my electricity consumption. And that's possible, and these days are a little bit expensive, but it's coming along, and this industry is really evolving very fast. And we have different types of batteries, different types of configuration. Companies are offering those. Whatever you get from the solar panel, some of it you use, some of it goes to charge the battery during the day, and if you have still excess, you send it back to the grid. And then at night, or if it's a blackout, depending on how many of these batteries you have and charged, to provide you electricity. Okay, so this will end the chapter about energy and work, and please go back and review and read it, and I will see you next time. Have a nice day or night, and bye-bye.